Good evening, everyone. Good afternoon, everyone, and welcome to this lecture. We have finished gravitation and now we venture into the wave part. So, we'll try to wind it up as soon as possible. This is SHM, Simple Harmonic Motion. I guess you have heard about simple harmonic motion. You have an idea about simple harmonic motion? Yes or no? Eh? No one has an idea. What is a simple harmonic motion? Hmm? You would have heard about simple harmonic motion. Yes or no?
Yes, sir.
What do you mean by a simple harmonic motion? Okay. Now, as soon as we get into this simple harmonic motion, first of all, let us try to understand the first heading. And the first heading that we will write is periodic motion. Periodic motion. This is how we start simple harmonic motion. Now, you must all be aware of what a periodic motion is. Yes or no? You all know what a periodic motion is? What do you mean by a periodic motion? Anyone? What is a periodic motion? No idea?
Sir, which has regular intervals of time, same motion in regular intervals of time.
So a motion which repeats itself after a particular interval of time is known as periodic motion. Some people also call it harmonic motion. It is not simple harmonic though. It is known as periodic or harmonic motion. We rather not use the term harmonic here, but we use the term periodic. It's a motion that repeats itself after a fixed interval of time, and that fixed interval of time is known as the time period. We know this, yes or no? That fixed
Sir.
interval of time is known as periodic time period. We have seen this periodic motion in our uniform circular motion. T was time period that was equal to 1 by f, and this time period was 2 pi by omega. Yes or no?
Yes, sir.
So same thing, omega. Here T is known as the time period, f is known as the frequency. We all know this. Yes or no?
Yes, sir.
T is known as the time period, f is known as frequency, and omega, in that chapter we are calling it as angular velocity. But here, instead of calling it as angular velocity, because angular velocity might be used for something else, we will call it angular what? Angular frequency. Omega would be known as angular frequency. Angular frequency. So this is how we start with our concept of simple harmonic motion. Now, the example of this periodic motion is any motion that repeats itself after a certain interval of time. The motion of your seconds clock, hour clock, minute hand, motion of the spinning of Earth on its own axis, the motion of moon around Earth, the motion of Earth around Sun. All of these are periodic motion. We all understand this, yes or no? You all understand this, yes
Yes,
or
sir.
no?
Yes, sir.
Okay, this is periodic motion. Everyone understands this. Have you written this down?
Yes, sir.
And the next thing that you must understand is known as oscillatory motion. oscillatory motion or oscillation, or sometimes we also call it vibratory motion or vibration. When do we say a motion is oscillatory, or it's known as an oscillation or vibratory motion? Yes.
To and fro motion, sir.
To and fro motion about a point. Now this to and motion can be a linear motion, or it could be in terms of angular motion. So whenever we have a to and fro motion, to and fro motion is known as oscillatory. To and fro motion is known as oscillatory motion. Now this to and fro motion, the important thing that you must remember about this to and fro motion is that it may or may not be periodic. It may be periodic or it may not be periodic. To and fro motion, it may be periodic in nature, it may not be periodic in nature. Now if I draw the diagram of a periodic motion, uh, it oscillates about a point, to and fro about a point. This point may be known as the mean position, or sometimes it is also known as the equilibrium position. Mean position or equilibrium position. Then you have one extreme and the other extreme. This A and B are known as the extreme positions. We know this, yes or no? This A
Yes.
and B are known as this extreme position, and the distance from O to A is known as the amplitude. So I've written it as A. Let me not write it as A, because then let me write it as X and Y. Then this distance from O to X is known as the amplitude of this oscillatory motion. We know this, yes or no?
Yes, sir.
Amplitude of an oscillatory motion. Now, this is what an oscillatory motion is all about. It oscillates about a given point, right? Extreme position, mean position, equilibrium position. Everyone knows this, right? Now,
Yes, sir.
we have noted this down. Yes or no?
Yes, sir.
Now we come to the next heading, which is known as a simple harmonic motion. Now we come to the next heading, which is known as a simple harmonic motion, or in short, we call it the SHM. Simple harmonic motion, or we call it SHM. Now, what do you mean by this SHM? What do you mean by this SHM?
Combination of oscillatory and periodic motion.
Combination. Okay, so now remember, whenever we use this term harmonic for any motion, if we use this term harmonic, it basically means, whenever we use the term harmonic means, harmonic motion means that motion can be expressed. Harmonic motion means the harmonic motion can be expressed as a sine or a cosine wave. Sine or a cosine wave. Any function, no, any motion that can be expressed in terms of a single sine or cosine wave, you must add this single sine or a cosine wave, then that motion becomes simple harmonic motion. Now this SHM is the simplest form. SHM motion, simple harmonic motion, is the simplest form of periodic or oscillatory motion. Is the simplest form of periodic or oscillatory motion. Now we will understand more about this SHM, but here we can understand whenever we think about this SHM is of two types. The simple harmonic motion is of two types. Simple harmonic motion is of two types. The first type is known as a linear SHM. The first type is known as a linear SHM. Now what happens in this linear SHM? In this linear SHM, the particle moves to and fro about a fixed point and it moves in a straight line. So this type of SHM is known as a linear SHM. We will have to understand both type of this SHM and we will be doing that, don't worry. Just note it down, the two types of SHM right now. The first type of SHM is known as linear SHM and the second type of SHM is known as angular SHM. So what happens in an angular SHM and what happens in a linear SHM? You can see this. If you have a bob attached to a spring and this moving like this, that is the simplest example of a linear SHM. If you have a simple pendulum, the simple pendulum is oscillating, that motion can be called as an angular SHM. Linear SHM, angular SHM. We'll be doing both of these SHM, whether it is linear SHM or angular SHM. We will try to cover both of these SHM in our discussion. Have we noted it down, everyone?
1 minute, sir.
Okay. I'll give you 2 minutes. Once you are done, please let me know. Okay. Now, as soon as we get into SHM, we must understand some important points about SHM. So, what are the necessary conditions for an SHM to happen? The first condition for an SHM to happen, this SHM is obviously, SHM is a periodic motion. SHM, simple harmonic motion, is periodic motion as well as it is oscillatory motion. Periodic motion as well as it is an oscillatory motion. Everyone understands this, I think, you know?
Yes, sir.
Okay. Now, for this motion to be, this motion is periodic and oscillatory. Now, what differentiates it from this periodic motion or an oscillatory motion? Now, any periodic motion or any oscillatory motion may not be in periodic motion. It is an oscillatory motion as well. Whenever we have an oscillatory motion, let me go here to this oscillatory motion. Whenever we have this oscillatory motion and the particle is doing oscillation, if it is at some point, let us say this point, the particle is at this point, it may be moving towards the extreme position, it may be moving towards the mean position. That is not the point of concern. It may be anywhere between the mean position and the extreme position. Whenever it is anywhere between the mean position and the extreme position, there is a force which always acts on the particle, and this force tries to bring the particle back to its original position. This Fr, or this force, is known as the restoring force. Restoring force acts on a particle. Whenever it's an oscillatory motion, a restoring force acts on the particle which tries to bring the particle towards the mean position. So the direction of this restoring force is towards the mean position. If there is no restoring force, the particle will never come back to its mean position and the motion cannot remain oscillatory in nature. Now, what makes the SHM special is the restoring force is directly proportional to the negative of the displacement of the particle. That is what makes this simple harmonic motion special. If I draw the diagram of a particle executing SHM, and O is the mean position, and the particle is somewhere here whose displacement from the mean position is x, it will always experience a restoring force which will be directed towards the mean position. This force makes this motion simple harmonic because this force is directly proportional to negative of the displacement. Why we are saying negative of the displacement? Because if the displacement is towards this side, force will act. If the displacement towards left, force will act towards right. Similarly, if the particle is here at point B and the displacement is x, you can see the displacement is on the right side, but the restoring force is on the left side. So this is what makes this motion simple harmonic. This F should be, there must be a restoring force acting on the particle, and this restoring force acting on the particle must be directly proportional to the displacement. Direction wise, it must be opposite to the direction of displacement. Force is proportional to minus x, or you can write this force as minus kx, where k is known as the spring constant. No, we are not going to call it the spring constant. This k is known as the force constant of the SHM. This k is known as the force constant. This is known as the force constant, and because of this, the particle will be accelerated, and you can write the acceleration as minus k by m times x. This minus sign only indicates that this force is opposite to displacement. Do we understand this?
Yes, sir.
So this is what that makes simple harmonic motion different from your normal vibratory motion or oscillatory motion. Now, there are more points that you must remember about this. For example, in a simple harmonic motion, and we will come across these points one by one. Um, for a motion to remain simple harmonic, the non-conservative forces must be absent. Non-conservative forces must not be present. Or if they are present, the work done by these non-conservative forces is zero. So basically what we want to say is the mechanical energy should remain constant. If non-conservative forces are present, the mechanical energy will not remain constant and the motion may not remain simple harmonic. So mechanical energy should remain constant. At the same time, in most of the cases, the amplitude should be small. The amplitude should be small. If the amplitude becomes large, then the motion may not remain a simple harmonic. Now, if these conditions are fulfilled, what are the conditions that are fulfilled? That there must be a force acting. The restoring force must be proportional to the displacement. Vector wise, force vector must be proportional to minus of displacement vector. Non-conservative forces should not be present. Amplitude should be small. A motion may become simple harmonic in nature. Here we are talking about the linear simple harmonic motion. Well, in case of angular simple harmonic motion, we can write similar thing. If this is an angular simple harmonic motion, we will take instead of displacement, we will take angular displacement, and there must be a restoring torque which will try to bring the particle back to its original position. This restoring torque must be proportional to minus of this angular displacement. Do we understand this? Or you can write this torque as minus c theta, where c becomes torsional constant. You can call them torsional constant, and then you call this then your angular acceleration alpha. You can find out the angular acceleration. We will come to this angular SHM once we finish with this linear SHM, but all the points about angular SHM and linear SHM are same. I'll give you 2 minutes to note them down. Now, whenever we talk about this simple harmonic motion, there would be an equation of simple harmonic motion. So the next heading that we are going to write is the equation of simple harmonic motion. First, we will try to concentrate ourselves on linear SHM. Once we are done with the linear SHM, then we will try and move on to your angular SHM. So first, write the equation of SHM. Equation of SHM. Now, how do we write the equation of this SHM? We can start with F is equal to minus Kx. Now, this F is the restoring force, K is our force constant, X is the displacement from the mean position. Now, they can write this as m into d2x by dt square is equal to minus Kx. Do you understand how I've written this? I've written acceleration as a second derivative of position or displacement. Do we understand this?
Yes, sir.
Now I can just take the terms together and write it in this form. When I write this equation in this form, whenever I get anything in this form, that becomes equation of an SHM. This, my dear friends, is known as the differential equation of SHM. Differential equation of SHM. This is known as differential equation of SHM. Okay. Now, instead of writing this equation like this, I can write it in this fashion: d2x by dt square plus omega square x is equal to 0. Now, this is the form that you will find this equation written many times, where you can easily understand that this omega is root over k by m, and this omega, which is root over k by m, here we are using omega for angular frequency. So remember, this omega is known as the angular frequency of SHM, not the angular velocity of SHM. Angular frequency of SHM. Now, if I solve this this differential equation, which is basically an exercise in maths, and we will not go into that exercise in maths, we can just write the final equation that you will get as this one. You can write the displacement as a function of time, and the equation that we are going to get will be like this: x is equal to a sine omega t plus phi. We will get it in this fashion, where we will try to understand each and every term as it comes. Have you noted this down? Have you noted this down?
Yes, sir.
Okay. Now we will try to understand each and every term together. So you can write the heading terms in SHM or whatever you want to write. Now you can have this simple diagram that is going to tell you mean position, amplitude, extreme position. We have seen this, yes or no? So basically this is showing you how this particle is moving. It is going from mean to extreme, then extreme to mean, then from this mean to that extreme, then coming back. This is how the equation look like. Now the first term is displacement, and remember, the displacement of a particle in SHM is always calculated from which position? Remember, it is always calculated from the mean position. So the displacement of particle in SHM is always calculated from the mean position. X is equal to a sine omega t. It is always calculated from the mean position. Do we remember this? Yes or no? Do we understand this? Yes or no?
Yes, sir.
Then the second thing that you must understand is the amplitude of SHM. It is the maximum displacement of particle from the mean positions. We all know this, yes or no?
Yes, sir.
Make it bigger so that you can see it. It is the maximum displacement of particle from its mean position is normally denoted by letter capital A. So this capital A that you see in this equation is actually your amplitude. Everyone knows this, yes or no?
Yes, sir.
Then you have the next term, which is known as angular frequency or omega. We all know this term omega. Previously, we were calling it as angular velocity. Now we are going to call it as angular frequency. Everyone understands this, yes or no?
Yes.
Then we have the next term. I hope everyone is writing these terms. In this chapter, the only thing that is important is for you to understand these terms. If you understand these terms, things become very simple. The next term is frequency, number of oscillations in 1 second. We have already seen all these terms. I'm just going through them and then I'll give you time to note them down. The last term is time period. Everyone knows these terms, yes or no?
Yes, sir.
I'll give you 2 minutes to note them down. Let me just give you a question based on what we have learned till now. Remember, the most important part in SHM is understanding this equation, understanding the terms, and how are you going to use those terms. If you understand it, the topic becomes very simple. If you don't understand it, well, the topic becomes very confusing. So this is the first question that is coming for you. For a particle executing SHM, the equation is given by this. What is the time period of the particle? I'll give you 2 minutes to solve this. That is correct. How did you get it? So you can compare it with the original differential equation. And if you compare it with the original differential equation, what will you get? You will get omega square equal to 4. Yes or no? That means your omega will, that means your omega would be equal to 2. Your time period is 2 pi by omega, and that becomes pi. That is how you find out. That is how you find out the time period from this given equation. We understand this, yes or no?
Yes, sir.
Okay. The next thing that we are going to understand is what do you mean by phase, and this is a very important thing that is going to come many times in this chapter and the coming chapter. Phase, the physical quantity which tells us the state of motion of the particle, its position, its direction, its velocity, even its acceleration, is known as phase. Now in that equation of y is equal to, or not, I am writing y is equal to, x is equal to a sine omega t plus phi. Whatever we saw inside that sine, that's an angle. Omega t plus phi is an angle. That omega t plus phi is known as your phase of the particle. Do we understand this?
Yes, sir.
Remember this phase, because this phase is going to be a very important term. This phase is going to be a very important term that is going to come many times. And in this equation, we also see a constant, an angle phi. This phi is known as the initial phase of the particle. This phi is known as the initial phase of the particle. This phi is known as the initial phase of this particle. Or I can say this is the phase of the particle at time t is equal to 0 seconds. At time t is equal to 0 seconds, the phase of the particle is known as the initial phase. I hope you understand what I'm saying here. Yes or no? No, yes.
Yes, sir.
This phase, initial phase, is also known as EPO. EPOCH. This is the next term that we use. We call it in the same phase. We call the initial phase as EPO. Have you noted it down? Now, if you have two particles executing SHM, if we have two particles executing SHM, say x1 is a1 sine of omega t plus phi 1, and you have the other particle as x2 is equal to a2 sine of omega t plus phi 2, and we are going to come across these terms a lot of time. Now, this pink one is the phase of the first particle, and this green one is known as the phase of the second particle. Then we have a term which is known as phase difference. Phase difference, delta phi. Phase difference, delta phi, is the difference in the phases between first and the second, or second and the first. If I subtract 1 from 2, it will be phi 1 minus phi 2. Phase of first minus phase of second, or phase of second minus phase of first. No matter how you do it, no matter how you do it, let me just call this as omega 1t, and let me call this as omega 2t. So omega 2 minus omega 1 into t plus phi 2 minus phi 1, that will be the phase difference between the two particles. Do we understand this? Yes or no? Do we understand this? Yes or no?
Yes, sir.
If omega 1 is equal to omega 2, then your phase difference delta phi becomes phi 2 minus phi 1. Do we understand this, or this is going above our head saying bye bye?
We understood.
Everyone?
Yes, sir.
This phase difference is going to come a lot of times. Now, there is a term that we call two particles are in the same phase, and there is a term which we call two particles are in the opposite phase. Can anyone tell me, when do we say two particles are in the same phase, and when do we say two particles are in the opposite phase? Yes, my dear friends. When do we say two particles are in the same phase, and when do we say two particles are in the opposite phase? When the phase difference between two particles delta phi is even multiple of pi, we call them to be in the same phase. If it is an odd multiple of pi, we call them in the opposite phase. And remember, this is a very important consideration. Phase difference, same phase and opposite phase. I'll give you 2 minutes to note this down. Now let us move on. Since we are doing this phase difference and this, there is a term that is going to come in the next chapter and so on, but we can do it here also. Remember, a phase difference of 2 pi, an important point, a phase difference of 2 pi is equal to a time difference of capital T, and this is equal to a path difference of lambda for a wave. What do you mean by all these things that I have written? And it becomes easier for you to understand if you see a sine or a cosine wave. Now, if you see a sine or a cosine wave, the sine or the cosine wave looks like this. Yes or no? Yes or no?
Yes, sir.
Now, if I talk in terms of time, if the time here is 0, the time here is capital T. Yes or no? Time here will be T by 2. Time here will be T by 4. Time here would be T by 2. Time here would be 3T by 4. Yes or no?
Yes, sir.
If I talk about the same thing in terms of an angle, if the angle at mean position I call 0, then it goes to the extreme, it will become 90. When it comes back, it becomes 180. We're talking about one oscillation. So if I say the angle here is 0, the angle here becomes 2 pi because it moves one circle or one rotation or one oscillation. Do we understand this? In terms of angle, if I talk. So angle here that it turns is pi. Angle here, what it turns is 3 pi by 2. And angle, in terms of angle, it is pi by 2. The same thing if I talk in terms of distance. We can call from here to here. The distance of a wave would be lambda. From 0 to lambda. Lambda is known as the wavelength. It's not going to come in SHM, it's going to come in the next chapter. Then the value of lambda here, I mean the distance in terms of path will be lambda by 2. So basically, what we are going to see is a relation between phase difference, time difference, and path difference. Do you understand what I have written here? Yes or no? From here, I can convert anything into anything. Any phase difference into time difference, any time difference into path difference. How I am going to do this? Phase difference divided by 2 pi will be equal to time difference divided by t will be equal to path difference divided by lambda. Do we understand how I've written this? We get this? Yes or no, everyone?
Yes, sir.
Anyone understand this? Anyone having any doubt? Okay, I'll give you 2 minutes to note it down. Since we have now understood the basic terms that we are going to use in SHM, now we can go and see the equation of SHM once again. The next heading that you are going to write is displacement in SHM. Displacement in SHM. Displacement in SHM. Now, the normal equation of displacement in SHM will look like this. X is equal to A sine omega t plus or minus phi. Yes or no? And we know all the terms in this equation. Now, if this SHM starts from mean position, and velocity is towards right, that means this is the mean position O, and the SHM starts in this way. Then the equation of SHM can be written as X is equal to A sine of omega t. This will give me the value of the displacement of the particle at any given time with this equation. Now, if SHM starts from mean extreme position, Say for example, the SHM starts like this. What will be the equation of SHM? And I will just rely on your common sense. What should be the equation of SHM if it starts from this extreme position? Yes.
Minus AS. Minus.
Remember, the displacement is always measured from the mean position. It's never it is never measured from the extreme position. It's always measured from the mean position. Yes, now give me the answer. In this case, the equation of SHM will become A sin omega t. It will become A sin omega t plus pi by 2 because it has now moved one side. So now you can write the equation is A cos omega t. This becomes the equation in case number 2. Do we understand this?
Yes, sir.
Now the third one you will have to give me. If the equation, if the SHM starts like this, it starts from the mean position but it is going towards left, what will be the equation of SHM in this case? Yes.
Minus A sin omega t.
Minus?
A sin omega t.
How did you get minus A sin omega t? This equation can be written as x is equal to A into sin omega t plus pi. Has gone 90 degrees, come back 90 degrees. So it can write it as minus A sin omega t. Do we understand this? Yes or no?
Yes.
Next case. If the equation begins from this point like this, then what will be the equation? Yes. It will be equal to x is equal to A again sine omega t plus 3 pi by 2. Or I can write it as minus A cos omega t. Do we understand how I have written these equations? Huh?
Yes, sir.
Pakka?
Yes, sir.
Well done. Then I have a question for you.
Yes, sir.
You'll have to write the equation of SHM for this particle. How will you write the equation of this particle? I'll give you 2 minutes to think about it. So how do you find this out? No, see, even the node became bored. You can't do this. It became bored and it shut down. How do you do this? I don't know what is there, so I just write the simplest possible equation. The equation of SHM should be in this type: sine of omega t plus phi. In all of the above cases, I don't think whether you have noticed it or not, I found the value of phi. I found the value of phi, nothing else. You just have to find the value of phi at time t is equal to 0. The displacement is a by 2. So a by 2 will be equal to a sine phi. So from here I can get the value of phi. What is the value of phi? Yes or no? What is the value of phi?
Sine inverse 1 by 2.
How much is that? How much is that?
Pi by 6.
Pi by 6. Is that the only value of phi possible?
No, sir.
There is one more value of phi possible, right? What is that? Pi by 6 is 30 degrees. Or it will be 5 pi by 6. 150 degrees. Sine of 150 degrees is also, my dear friends. Yes or no? Sine of
Yes.
150 degrees also is. Now you have to decide whether it is pi by 6 or 5 pi by 6. Which value should I put here? Pi by 6 or 5 pi by 6?
Pi by 6.
Why 5 pi by 6, not pi by 6?
Sir, it is moving from minus lambda to lambda.
Minus lambda to lambda. Okay, you can say this in that way, but I don't think you have understood the concept. First, it goes from here to here. So the angle becomes 0 to 90. Then it goes back from here to here. So now the angle has to be between 90 and 180. Between 90 and 180. And the only angle between 90 and 180 is 5 pi by 6. So my dear friends, the equation of SHM would be x is equal to a sine omega t plus 5 pi by 6. That will be the equation of SHM for this particular condition. Do we understand this?
Yes.
Yes or no?
Yes, sir.
Okay. Please note it down.
Done, sir.
This is the condition now, sir. At time t is equal to 0, particle is here, moving like this. The displacement from the mean position is given as a by root 2. I hope you understand this. Now I want you to write the equation of SHM. In this case, I'll give you 2 minutes to do it. And I hope you have understood the concept. Can anyone explain how did you get the answer as 5 pi by 4?
Sir, at t equals to 0, x is a by root 2.
minus a by root 2 actually.
Sir, that is minus a by root 2.
Mm.
So sine will be, sorry,
Yes, say na.
sir.
Just say. So you were saying something, na? How
Sir,
did you get 5 pi by 4?
Sir, whole explanation is changed due to that minus sign. So
No, the
it
explanation has not changed. The explanation makes
again.
sense because of the minus sign. Now, that is why I asked you the answer. Sometimes the answer does not make you understand what you have done. Getting the right answer is not the logic. Getting it in the correct way is the logic. A is minus 1 by root 2 because what I am assuming here is I am assuming that this direction is taken as positive and the other direction is taken as the negative one.
Negative, yes, sir.
Now, can you explain how did you get it?
Sir, sine inverse 5 is sine inverse of minus 1 by 2.
1 by root 2.
1 by root 2, and there are two possibilities.
Third and the fourth quadrant.
Third and fourth quadrant.
Which quadrant is this? Third or fourth?
Third quadrant, sir.
This is in the third quadrant. Do not
Third
say, sir,
quadrant.
second quadrant. Quadrants are not like this. Quadrants are decided. This is the first quadrant when it is going like this. When it's coming back, that's the second quadrant. When it's going from there, that is the third quadrant. And when it's coming back, it is the fourth quadrant. Do we understand this? So it is going
Yes,
to
sir.
the other extreme. It's in the third quadrant. That is another way of understanding the same thing. Do we understand this or this is gone above it saying bye-bye?
Understood, sir.
Pakka? So
Yes,
it
sir.
only makes sense because of a by root 2 is negative. That's why it is coming as the third quadrant wala angle. Got this? So plus
Yes,
1 by
sir.
root 2 will not give you this answer. Anyways, chalo. Now comes this question. Question number 3. Let's see who gives me the answer. A particle executes SHM of time period capital T. Find the time taken by the particle to move from extreme position to x is equal to a by 2. To half of the amplitude. From the extreme position to the position where the amplitude is half. And you have 2 minutes to show me your talents, else I will show mine. Everyone understands the question? Yes or no?
Yes,
So
sir.
your answer should come in terms of capital T, remember. I will give you this as an homework. So what you can do is try it at home because I will discuss this question or these type of question in detail and try to make you understand how these questions are done. Okay, so we'll discuss these questions in detail in the next class and I'll give you more of this type. Try and solve this question and I'll see you back tomorrow.
Sir, T equals to T by 6, sir.
T equal to T by 6. How did you get it?
Sir, at T, the particle taken to be moved from extreme to mean, no, sir.
Right.
At T equals to 0, it is at extreme position, that is displacement is minus A, sorry, plus or minus A, that may be taken any extreme position. At T equals to some time T, so it say let small t, sir. Let time equals to small t, it is at a by 2. So displacement can be plus a by 2 or minus a by 2. If we take extreme position as plus a, the displacement will be a by 2. So we can get their phases.
Okay, that
Both
is correct.
phases can be found, and you have given that formula, sir. Phase difference by 2 pi equals to time difference by total time.
Okay, we will do this. Don't worry. I
Okay,
got
sir.
your concept. That is correct. I will just try to make you understand the same thing, and we will do it in the next class. Okay, and I'll give you more questions on this. Okay. So then, we'll discuss these questions and make it clear via diagram. It will be easier for you to understand. So we'll do it in the next class. Okay.
Okay, sir.
Okay then. This is the beginning of SHM. Remember, the most important thing about SHM is the equation of SHM. If you understand that equation, you are good to go. So take care, and I'll see you in the next class. Bye bye.